So hello everyone, my name is Kormu from the University of Helsinki, and I'm here to talk to you about bubble nucleation and why you should use lattice simulations to calculate bubble nucleation rates rather than perturbation theory. This is trouble in the bubble, testing bubble nucleation rates. So without further ado, let's get started and look at first order phase transitions and their mechanics. So we have a field phi that goes through a phase transition, and it has this potential Vf that develops a potential barrier as we get closer to the critical temperature where the phase transition happens, and as we dip below the critical temperature we have these two minima where the universe is now actually trapped in false vacuum or the metastable state. I will be using these terms interchangeably for the duration of this talk. So eventually we want to get to the lower energy state of the symmetric or the stable phase. So we have two options. We can either tunnel through the potential barrier or we can thermally fluctuate over it. And as we do this, we have these bubbles of the stable phase that then form and nucleate, and then they start expanding, colliding with each other eventually, and these collisions could source gravitational waves. So the gravitational waves would come from the turbulence or sound waves that these bubbles create in the early universe plasma. So this is really a cosmological equivalent of boiling of water. So that is also a phase transition, so this is just a tad more complicated than this. So what I am interested in are these stochastic gravitational waves, or the background that they form, that has started from the very early universe and could still be detectable even today. So what I'm looking forward to is this LISA space mission that is launching in the mid 2030s that could actually be able to detect a signal that has traveled from those very early stages of the universe until today. And LISA is the space triangle that follows Earth on its orbit around the Sun, trailing behind it at a 20-degree angle. So LISA's main purpose is to detect astrophysical sources. So it's also a question of how can we get this stochastic gravitational wave background from under all the astrophysical noise. And we also need to be able to estimate this stochastic gravitational wave background as accurately as we can so we can nail down the shape of it. So the stochastic gravitational wave background, we start from a particle physics model, then we do dimensional reduction. So we go from 4D to 3D theories, and then we simulate that to get the phase transition parameters. So the transition temperature, inverse duration of the transition, transition strength, bubble wall speed, and so on. And from there we can go to the real-time cosmological simulations where we look at more at the bubble dynamics itself. So not the nucleation anymore, but rather how do the bubbles behave when they collide and expand. And then finally, with all that info put together, we can get this cosmological gravitational wave background. So now the problem is that these phase transition parameters actually affect the shape of the stochastic gravitational wave background. So for example, the alpha, so the transition strength, brings it up, and the other parameters, for example, the beta, so the inverse duration of the transition, brings it down. And the thing here is that all these phase transition parameters, they depend on the bubble nucleation rate itself. So this kind of raises the question of, if our bubble nucleation rate calculations are not accurate, how accurate are our cosmological predictions actually? Other thing is that we have been using perturbative calculations in order to estimate these bubble nucleation rates, and these perturbative methods suffer from problems that have to do with the details of the, for example, the semiclassical approximation that you do. So here we have a stochastic rotational wave background, a signal, as a function of the frequency. And you can see how large these error bands are when calculated from one loop versus two loop, and how much they affect the shape of it. And these error bars are really reflect the fact that usually when you do these perturbative calculations, you do not calculate the dynamical part of the bubble nucleation rate. You only calculate the statistical part. So what you're missing is the dynamical information of the system. And this is due to many reasons. The dynamical part is really difficult to calculate analytically. So besides the perturbative calculations that need testing, you can also look at bubble nucleation in a lab setting. So the nucleation theory is essentially the same in the lab and in cosmology. So people have been studying these superfluid helium-3 transitions, for example, but there's a long-standing discrepancy in those. And then we also have other experiments setting up, like ferromagnetic superfluids and other ultra-cold atomic gases, and very excited about these nucleation rate tests in the lab. That is one of the reasons also why these bubble nucleation rate calculations are interesting. And one more thing, besides the stochastic rotational wave background signal and the perturbation theory and this lab, is the baryogenesis, because baryogenesis, also the dynamics of it, depend on the bubble nucleation rate. So we have four things that play into why bubble nucleation rate calculations are important and interesting right now. So what we have looked at is something called the real scalar theory. And if you want to look at the equilibrium dynamics, I refer you to this paper here. But we are looking at bubble nucleation specifically here. So the real scalar theory is a toy model that has all the key features of beyond the standard model theories. So it has a potential that has a 3-level barrier, and it's a strong phase transition compared to, for example, these radiatively induced transitions that have been studied before. And the perturbative expansion is also simpler, so we should understand the dynamics of the system relatively well. And here we have the Lagrangian with the interaction terms. You can couple it to standard model via Higgs portal interactions, for example, and such. And then we have the potential, and here we have the model parameters. So now that we have this written down, this 4-dimensional theory, we want to reduce it to 3-dimensional theory because it's a lot simpler to simulate that on the lattice rather than this full 4D theory. So what we do is we do dimensional reduction, so from 4D to 3D, because at high temperatures the system looks 3-dimensional. So you integrate out the heavy modes, you match the correlation functions, and then you are left with this 3-dimensional Lagrangian. And from there you can discretize this to the lattice. And our lattice action reads, so it has sum over all the lattice sites with the lattice spacing A. And then we have this renormalization counter terms from Z phi and M. And then we have the lattice parameters. And then you put this on the lattice and you simulate it. So the bubble nucleation rate is built out of two main kind of factors in a sense. So it has the dynamical information and the statistical information. So the statistical part is usually what is calculated using perturbation theory, etc., etc. And the dynamical part is then really difficult to calculate in perturbation theory. We can actually do both of these. They are not one-to-one on lattice and on the perturbation theory side, but for the sake of this talk, we will just refer to them as statistical part and dynamical part. So we start simulating the statistical part. So how do you calculate bubble nucleation rates in the lattice? So Kari Rummukainen and Kai Moore came up with this multi-canonical Monte Carlo method for bubble nucleation rates in the early 2000s. So what we do is we pick an order parameter of the system. It doesn't need to be a true order parameter. It just needs to be able to distinguish between the metastable and stable phase. So you have this probability distribution that has this two-peak structure. And in the between these two phases is the exponentially suppressed mixed phase that we call critical bubble. And you need the multi-canonical Monte Carlo because these exponentially suppressed mixed phase configurations are incredibly difficult to simulate due to suppression. So with those simulations, you can calculate the probability of those critical bubble configurations, and those set the upper limit of your bubble nucleation rate. And you normalize this to the metastable phase peak. So then you have your statistical information of the system. What we also do in this Monte Carlo side of things is that we draw these separatrix, also sometimes called as transition surface configurations from small area around the critical bubble. The small area is marked here by epsilon. So we draw these configurations that we can then use in the real-time evolution or in the heat path. So what we do next is to determine the dynamical information. And we do that by evolving these bubble configurations forwards and backwards in time. And then you just glue these trajectories together. So here, for example, we have the order parameter as a function of the simulation time, and the starting point is the configuration that we have just gotten from Monte Carlo. So we start from there, forwards in time, then you reverse the momentum and start from the starting point again and go backwards in time, and you glue these trajectories together to determine if it has tunneled or not. So here, for example, we have one that has started from the metastable phase and gone to the stable phase, and one that has started from the metastable phase and also gone back to the metastable phase. And from there, you can determine this fraction of the tunneling fraction. So you have delta tunnel, which is 1 if it tunnels, and is 0 if it doesn't. And you get this dynamical information based on these trajectories. So now you have the tunneling fraction, but you also need to know how quickly do you actually pass the order parameter. So we have something called the flux, the rate of change of the order parameter, and you can actually calculate this analytically because the momentum field is assumed to be Gaussian. So we have something that goes to square root 8 over pi and the volume times the order parameter value at the critical bubble plus a squared. So the a squared is just some value that you have picked. It comes from our choice of the order parameter. I will explain a bit more in the next slide. But once you have all these different parts, you can compute the full rate. So you have the statistical information of the critical bubble probability, the flux, and also then the dynamical tunneling fraction. And the 1/2 comes from the fact that the tunneling fraction actually double counts the trajectories, because you want ones that have started from the metastable phase and ended up in the stable phase, because the critical bubble configurations are equally likely to go either direction, so you only want the ones that actually do it in the correct order, so to speak. So regarding the order parameters, this is actually rather non-trivial. So there are better choices for order parameters than others. So you pick one that should be able to distinguish between the two phases, so the metastable and stable phase. The problem is that when you go to larger box sizes, these fluctuations about the metastable phase, what we call bulk fluctuations, actually start to dominate and can bury under the critical bubble branch that is exponentially suppressed. So in order to combat that, we tried a bunch of different order parameters, but we found that setting the parameter A that you saw earlier into the symmetric peak value, this actually reduces these bulk fluctuations dramatically, and we can go into bigger volumes that is needed, for example, the volume limit. So let's talk about results. Here we have the continuum and volume limit plots. So we have the logarithm of the nucleation rate as a function of the lattice spacing. From here we see that we are already at the continuum limit at A is 1.5, and we perform the rest of our simulations at that lattice spacing. So we fit a cubic into these lattice spacing points because we use something called A squared discretization. So we should see the first dependence on the lattice spacing at A to the third. So hence the cubic fit. We also note that the inverse screening mass of the system is marked here by this dashed line, and we expect the cubic form to break down at that due to the fact. We also have this linear order parameter here, which reflects our initial choice of order parameter. So we can see that this one that has suffers from the bulk fluctuations has large error bars compared to the ones that we have here, so we much reduce the error in our simulations. So the continuum, the volume limit plot, then we fit an exponential to it because the Euclidean model has no massless modes, so the long range correlations die off exponentially with distance. So here we have the different points and the bubble nucleation rate of minus 74.09 based on our simulations, and that is the final answer. The bubble nucleation rate is that. From there, because we have only simulated one parameter point at a certain temperature, we also want to be able to show you a comparison with perturbation theory where we have the logarithm of the bubble nucleation rate as a function of temperature. So we take this point that we have studied in the infinite volume limit. It's here on the orange, it's a triangle, and then we re-weight it to different temperatures. So the curve above it is the one loop result. And so it's the full one loop result that you can get, for example, from this Python package called BubbleDet. So it has the dynamical and statistical parts calculated numerically in the BubbleDet Python package. Then above it, we have the local potential approximation, and the error band here reflects the different choices that you can make in that approximation to get rid of these imaginary parts that eventually turn up. And then we have the tree-level approximation that just assumes that the dynamic prefactor is t to the fourth. So tree-level is 100% away from our results. One loop estimate agrees qualitatively the shape of the curve is very similar. However, it is still 20% away from our result. And this is in logarithmic space, so the one loop result is actually 10 to several away in bubble nucleation rate. Now, this is quite surprising, and it kind of raises the question of, do we fully understand bubble nucleation? We have chosen our simulation parameter point based on the fact that we know that in latent heat, the exact same point agrees really well within 1% in perturbation theory and lattice. They agree within 1% in latent heat. And then when we look at bubble nucleation, we are suddenly 10 to several orders of magnitude away from the one loop result. There's a couple of things that could be responsible for this. So we simply might need the next loop order. But there are also other possibilities that may be worthwhile to consider. So we might have the case that the semiclassical approximation might break down, or that there are other relevant saddle points that should be considered in the calculation. Of course, most likely it is the case that we just need the next loop order here. In conclusion, our results allow to calibrate the uncertainty in the phase transition parameters obtained from the perturbative results. And the accurate computations of the bubble nucleation rate are important, for example, for the gradation wave power spectrum and baryogenesis and so on and so forth. And my one bubble takeaway, so the one thing that I want you to remember from this talk, is that nucleation rate calculations are inaccurate in perturbation theory, and lattice is significantly better. Thank you.